There you go.
Okay. Hello, everybody. My name is Damir Farizovic. Welcome to yet another installment of the Point Distributions webinar. Our today's speaker is Julian Hofstadler, and he will be talking about subsequences of random points. So please, Julian, the screen is yours.
Okay. Thank you for the nice introduction. I will share my screen now. And also let me first thank the organizers for giving me the opportunity to speak in this webinar. And thanks again for the nice introduction. As you told, today's talk is based on a subsequence of random points. So in particular, I will not present my own work, but I will just basically present the paper, The Power of Online Thinning in Reducing Discrepancy, which is due to Dwivedi, Feldheim, Gurel, Gurevich, and Ramdas. So I hope the pronunciation was not too bad. And what are we going to do today? First, I will introduce the discrepancy and present you some old results and what we basically know so far. Then I will discuss the technique called thinning, which is from their paper. And then to combine both of these topics, we will also have a look at the discrepancy of a thinned sample. So we are not too many people, and so I think it's just okay if everyone asks questions where they arise. And as I cannot see the chat, if there are questions in the chat, so would please one of the organizers just interrupt me to give me the question at any point. So let's start with the notation. We will always have a look at the d-dimensional unit cube and the point sets. I will denote them by Pn. They contain exactly n points. We consider the discrepancy with respect to axis parallel boxes. They will be denoted by this fancy E. And the discrepancy is given in the unnormalized version. So what does this mean? If we would divide this whole expression by n, then we would get somehow the normalized version of the discrepancy. This was the case, I think, in Matthias' talk, for example, when we were having a look at discrepancy on the sphere. But in order to stick to the notation from the original paper, I will use this form of discrepancy. And so what does discrepancy do? Basically, we just have a look at the axis parallel box and count how much points are in this box, and then we subtract the number of total points times the Lebesgue measure of this box. And if we take the supremum over all axis parallel boxes, we get the discrepancy. What do we know so far about discrepancy? There are some sets, for example, the Halton-Hammersley set. It's closely related to the Van der Corput sequence, which Luis presented on Wednesday. And these sets, I wrote the Halton-Hammersley set, but that's not quite correct because you're free to choose some primes. So it's better to say a Halton-Hammersley point set satisfies a bound of the following form. So we can bound the discrepancy from above by a constant depending on the dimension. In particular, it depends on the prime numbers you choose, and you can you have quite good estimates for these constants as well, but the main term is this log n to the d minus 1 here. And if we have a bound of this form for some set, we call it a low discrepancy set in general. And there are several ways to do so, which I will not go through now. On the other hand, we have this famous lower bound, which is due to Klaus Roth from 1954, if I remember right, who showed that for any point set Pn, the discrepancy is bounded from below by another constant depending on the dimension times a log n to the d-1/2. So there are improvements of this lower bound, but first of all improvements are not quite that big, even though it gets better. And the reason why I decided to present this bound is not because I don't like the authors of the other bound, but because this was just the first bound of this type, and it's also one of the most famous bounds in this topic, and so I just decided to give you this bound. What I want to mention is that in dimension 2, a result of Schmidt shows that a bound of this form, so log n, is a sharp bound up to constants for any set. So he bounded the discrepancy of any point set from below by a constant times log n. So in particular, the Halton-Hammersley point set is optimal in dimension 2. If we have a look at the dimension, I just go back, it's exponential here in this lower bound. So this is not quite satisfying, but there are also bounds in a high dimensional setting, or which are better in a high dimensional setting. To do so, I quickly have to introduce the star discrepancy. You don't have to remember it for the rest of the talk. But if we take the set of all axis parallel boxes, which are anchored in 0, instead of just the set of all axis parallel boxes, we get the star discrepancy. And it was shown by Heinrich, Nowak, Wozniakowski, and Wasilkowski that with high probability, we can just have a look at IID uniformly distributed points, and with high probability, we have a bound of this form. So an absolute constant times the square root of d times the square root of n. This is clearly very nice if we have very, very large d compared to the other results. And it was also shown by Hofstadler, I think it was in 2014, that the constant can be bounded by 10. But the proof of Hofstadler and the proof of this result, they are quite different. I can say both rely somehow on empirical process theory, but I also don't want to go into detail too much here. So let's talk about random points. There is one more result with respect to the star discrepancy I want to present you, which is due to Dörr. He showed that the expectation of the star discrepancy of a set of n points can be bounded from below by square root of d times square root of n and some other absolute constant. So to sum up, what can we do with random points, with IID uniformly distributed random points? We see they're quite good with respect to d compared to the other bounds, but still we always have this square root of n in any bound here. So one question would be, is it possible to also create sets with have a log n bound? Clearly, this can get worse with respect to d then. And what is also some kind of issue is that if we have a look at samples of IID uniformly distributed points, then it seems always, or at least very often, to be the case that there are small sets which contain very much points compared to the total amount of points, and some sets which are almost empty. So this is what I call clustering here. And in particular, it would be nice if we could reduce the probability of clustering. And what is the idea to do so? The idea is to reject some points or in each, or to have a look at each point one after another, and then to decide whether to keep him or not. And this is exactly what thinning is doing. So what do we need in general to be able to do this technique called thinning? We need a sequence of IID random points. They all should be uniformly distributed in the unit cube. I will call them xk. Then we need a sequence of IID random variables, uk. They should be uniformly distributed between 0 and 1. And then we need a sequence of measurable functions. These functions are called thinning functions. And how do they work? They look a bit strange at first, but the main idea is when using the kth function, we already have chosen k points. So we put them in here. Then we have a look at another point and measure how good is this point considering the already given points. So we map it just to 0, 1. And this collection, everything together, we call a thinning strategy. How does it work in general? We assume that in the kth step, we already know the points set 1 to set k, which we consider as good. So we already have chosen them, and we already have done a number of rejections. I will call it R. And then I can decide whether to keep or reject the next point, which is just xk plus R plus 1. And to decide what to do, I put everything in the thinning function. So the already chosen points, the point I want to decide whether if it is good or not. And if the thinning function evaluated at all these points is bigger or equal than uk, then we keep the point, and otherwise we just reject it. But if we reject this point, we will have to keep the next one. This is just also to ensure we have an algorithm which comes to an end and is also applicable if you use a computer simulation or something. One thing which I want to mention additionally is that if we have some lower bound on all thinning functions, fk, so in particular a bound of this form, we can bound all thinning functions from below by 1 minus beta, and beta is some constant between 0 and 1. Then we call it a 1 plus beta thinning strategy, and a sample, or if we choose set 1 to set n according to such a 1 plus beta thinning strategy, we call it a 1 plus beta thin sample. So how are we gonna use it? There is this lemma which is quite nice. I will explain why in a few moments, but let me just go through it first. Assume we have an absolutely continuous probability measure on the unit cube, on the d-dimensional unit cube. And assume the density satisfies an inequality of this form. So we can bound it from below and from above by beta. Then we know that the density minus beta over 2 defines a thinning functions. And we even know that the thinned samples are distributed with respect to this probability measure mu. So how can we use that? On the one side, we have a thinning strategy, which is pretty nice if for all applications which involve a computer, for example, because IID uniformly distributed points and the thinning technique by just applying a function on these points to choose them is not that hard to realize on a computer. But on the other hand, all the theoretical stuff we want to do, if we have a density of this form, we can just use everything from probability theory we know, and this is quite a lot. So in fact, we will try to create such densities. We will call them conditional densities. And before we can do so, I have some additional notation I want to give you. So in each step, we assume we already know the points set 1 to set t, which we consider as good points. And I will call these sets pt. Then I define some counting measure, which is just used to count points which fall into some set A. By the way, every time I speak of a set A or something, I always mean measurable set. But to not get too technical in every step, I will skip this most of the time. So what do we with this set pt? We try to create the density rho t for the t plus first point, and it may or even it should depend on this set. And I will use the following notation. So the probability that set t plus 1 falls into some set A, given the already known points set 1 to set t, is denoted by mu t of A, and it just comes from the density as one would expect it does. And additionally, I mean, I just told you thinning is a good idea. So additionally, we would like to have the inequalities which allow to use the lemma I just presented you. We're gonna create these conditional densities by dyadic intervals and half functions, or in the multidimensional case, dyadic rectangles and half functions. So let me just go quickly through the notation I will use. An interval I of this form I will call a dyadic interval. It has length 2 to the power minus L. And if we split it into its left and right half, which I will denote by I left and I right, then we can define the half function with respect to I, which is 1 if x is contained in the left half, and it's minus 1 if x is contained in the right half, and it's 0 everywhere else. These left and right parts of I are again dyadic intervals, but they have just half of the size of I. So in particular, they would have length 2 to the minus L minus 1 in this case. And this is also how we can define the order of H. So if H has exactly this form, then the order is L plus 1, and it comes exactly from the length of the left and right half. And moreover, this allows to define the constant function as half function of order 0. This is just because if we add the constant function to the set of all other half functions we have, and we do a proper normalization, then we would get an orthonormal base of L2. The multidimensional case is not that much different. We need d-dyadic intervals with corresponding length and their associated half functions. Then we can define a dyadic rectangle as Cartesian product of all these dyadic intervals. So it has size 2 to the minus L, where L is just the sum of these guys here. And the half function with respect to R is just given as the product of the one-dimensional half functions. And to define its order, we just sum up all the one-dimensional orders. And so it's again the case that the constant function is the only function of order 0. And also, to save some notation, I will use the following set. to just denote all half functions which have order between m and l. So are there any questions so far? Because my Zoom was just moving a bit, or is it fine? Okay, so I assume everything is fine. Oh, sorry.
Yeah, I think everybody's fine.
Okay. Well, then we move on and see how we can connect half functions and their conditional densities, which I spoke a few minutes ago. First of all, for any half function, we define the following sets, h plus and h minus, which is just somehow the positive and negative part of the half functions. And if we do not consider the constant functions, both of these sets are always have equal size in the Lebesgue setting. So this is important, in fact. And using this information about half functions and this definition, I define the counting measure with respect to a half function as the amount of points which lie in h plus minus the amount of points which is in h minus. So how can we use this quantity? Clearly, since they have the same size, if we have a good point set, this quantity should be close to 0 for any half function. And this is also the main idea. We want to create densities which try to always put points in places such that the counting measure for half functions gets close to 0. And this is done in the following way. The process we define is given by the following densities. We have 1 minus a normalization factor and then a sum of where I multiply a half function with the sign of the counting measure of the same half function. We will have a look at this quantity on the next slide. So it's very important to understand what these guys do in order to understand how this process works. But before I just, W of L is a normalization factor. Beta is free to choose as long as it's between 0 and 1. And this comes from the thinning we want to do. And L is depending on D, and is just the floor function of the log of T. So we see the more densities we have a look at, the more half functions we use in this sum. And we will also see in a few moments how we can use this property to see what is happening with this process. And to save some notation, I will just always write set for this process, and it comes from these densities. And I almost forgot, it's not hard to check that in fact the condition for the thinning lemma is fulfilled in each step. So indeed we get a 1 plus beta thinned sample where beta is free to choose. So now we have a look at this guy inside here, and remember we got a minus here. So what do we do inside the sum? If we have more points in h minus than in h plus at some time t, we increase, because there's another minus, we increase the probability that a point comes into h plus, and we decrease the probability that the next point comes into h minus. So this is intuitively just what we would like to have, because clearly this should be very good if we consider clustering. And if the roles of h minus and h plus are swapped, then it's just the same thing is happening. But we are mathematicians, so intuitively speaking, it's good, but we need to prove something. And indeed, we can prove the following lemma. So we set theta to beta over W of L. And then the process, which is defined by the conditional densities, which I just showed you, is theta balancing for the set H1L. So this is exactly the set which appears in the sum of the densities we just saw. What does theta balancing mean? In particular, this means if we denote by kappa the size of H plus and H minus, which is just half of the size of the support of H, then we see that the probability that a point falls into the support of some half function is just bounded by half of its support. So this sounds quite reasonable. And additionally, we have that if there are more points in H minus, then this quantity will just be -1. And we see that we just increase the probability of the t plus first point to fall into H plus. And this also depends on this theta here and on the size of the support of the half function. And if there are less points in H minus, it's just the same. Using this property, the balancing property, the theta balancing property, we can prove the following concentration property. Namely, if for some half function contained in H1L and for some time S, we have the following concentration bound, then we also know this concentration bound holds for later times t, for all later times. So this is a really nice property which a balancing process has, because we can just use it to give a first explicit concentration bound for the process set. We have a look at an arbitrary half function H, and we have a look at the following expectation, where we have the exponential of the beta over 2W of L. This was the normalization factor in the densities. And then we have a look at the counting measure at the time n for any half function. And this is just bounded by an absolute constant. If I remember right, it should be 600. At least it's computed explicitly in the original work. And we have the 1 over beta, which then just simplifies to W of L squared over beta squared. So, and also n, I forgot it to put it here, sorry for that. N is arbitrary, it has just to be a natural number. So how would one prove this lemma? If we consider half functions with large support, so what do I mean by large? Large somehow depends on how large n is. Then we use the balancing property. So in particular, the concentration property for balancing processes, which I gave you on the last slide. And for half functions which have already very small support, we use some kind of a domination argument by a binomially distributed random variable. And in both cases, we end up with this very nice concentration bound. But what is not good enough about this concentration bound is that it only holds for half functions. So with each half function has only a dyadic rectangle as support. And dyadic rectangles are not quite enough if we want to consider arbitrary axis parallel rectangles. So we have to introduce lattice rectangles. Lattice rectangle is, as the name suggests, it's just contained in the following, the corners are contained in the following lattice, it looks like this. And we know that if we have some arbitrary 2 to the minus L lattice rectangle, then there exist disjoint dyadic intervals, rectangles, D1 to dk, where k is not too large, so k is bounded by 2L to the d, and also the size of each dyadic rectangle is not too small, so they have size at least 2 to the minus L times d. And their disjoint union is exactly the lattice rectangle. What can we do with this result and the previous results? We can get a more general concentration bound, namely a concentration bound in terms of lattice rectangles. So for any 2 to the minus L lattice rectangle R, we have that the expectation of the exponential of, again, normalization factor, but here we already have the discrepancy, but R means that we are not taking the supremum, but we just compute it for the explicit rectangle. And what we get, this comes from the previous result of lattice rectangles being written as dyadic rectangles, is this factor here. But we can bound this expectation again by an absolute constant. I think it stays at 600 times 1 over theta, which was exactly W squared, W of L squared over beta squared. This proof is not that hard, in fact. Let us have a quick look. I think we have enough time for this. First, we have to estimate the discrepancy by writing it in terms of half functions. As I told you, the half functions, if we include the order 0 function, which is the constant function, are an orthonormal basis of L2 if we did some proper normalization. So this allows us to find some suitable coefficients, HAH, and then we end up, this comes just from triangle inequality, and first we write it, the discrepancy in terms of half functions by the basis property. And we also see that we in fact do not need all half functions, which is also quite a nice property if one goes through the proof. And we also have the following, let's call it normalization property of the coefficients, namely the sum of all coefficients can be bounded from above by 1. This allows to use Jensen's inequality in the following form, so that we can bound, we have this bound, and we already know the concentration bound for these guys, so we just apply the expectation on both sides, put it inside these sums, and we know concentration bounds for these guys, and these guys sum up to 1. And so that's basically the end of the proof. And yeah, the 2L to the D is somewhere hidden in these coefficients A. But it's a bit technical, but not that hard overall. And in fact, it's enough to present the main results. So the first main result is the probability of the discrepancy of the set Pn being large gets small very fast. So the constant Q is free to choose, and so it's pretty easy to see if we increase Q, then the right-hand side here decreases very fast. And so clearly if we have a look at the probability of the discrepancy being small, this we can bound it away from 0 and everything is fine. And in fact, this holds for any n. And an immediate consequence of this result is the next result, which is an asymptotic bound. Namely, if we consider the ratio of the discrepancy divided by log n to the 2d plus 1, and we have a look at the asymptotics, we can bound it from above by, in fact, this is a constant depending on d and beta. So it only involves the kind of thinning we did, where beta comes from, and their dimension. How can we prove the theorem? We use Markov inequality and the concentration bound to obtain a very similar result for lattice rectangles, and then we approximate arbitrary axis parallel rectangles by lattice rectangles, observe that everything does not get much worse, and then everything is done. So also quite a nice technique of getting to these results. But there are still some open questions which are due to numerical simulations which the authors did. So the first is they conjecture that the process Z should satisfy a better asymptotic bound, because here you see that log n is has a smaller exponent this term, and they think the asymptotics should still be finite. And they also present a second thinning strategy, which they call the greedy Haar strategy, for which they conjecture that the sequences which are produced are even better. So in fact, we only have a log n to the d plus 1 here. And yeah, we still have 10 minutes, I think, so we can have a look what is the greedy Haar strategy. Thereto I will just go back to the definition of the densities. So we have a look at this sum, but without the normalization factor. And on the next slide, we saw that each term inside the sum is -1 if the point is good and +1 if the point is bad. So this thinning strategy then uses the fact that if the sum is for a random point is overall positive, then there are many more Haar functions for which the point is bad than there are Haar functions for which the point is good, so we reject it. On the other hand, if the sum is negative, there are more Haar functions for which we consider the point as good, then there are Haar functions where we say the point is bad, so we keep it. And if it's equal to 0, then you just set your thinning function to 1/2, means you have a 50-50 chance of keeping or rejecting the point. So there are still some more open questions. So this was the greedy Haar strategy. Yeah, what is more to say about the greedy Haar strategy is that there is nothing proven for it, only results from simulations. But there are still some more open questions, which are, for example, at some point, the authors suggest that one could use better results. For example, the Jensen inequality. The authors think that one loses quite a lot there, and they also suggest to try to improve this. And they also think if you could do this, then you would get a better result in the end. And there are some other points one can find in their paper. I will not go through all of them now. But another point is are there probably other thinning strategies which perform even better? There too, let me go back on the previous slide. So we see in these asymptotic results, we are still away from having a low discrepancy point set or sequence, because this exponent is just too large. So another question would be, are there thinning strategies which could produce a low discrepancy point set or sequence? Or, I mean, is it possible to get these bounds which Heinrich, Novak, Wozniakowski, and Wasilkowski did? Because they just considered IID uniformly distributed points and did not worry about clustering at all. So it could be possible that by reducing this clustering, we should be able to do at least as good as they do, right? But we don't know, or I don't know at least. And you could also think about thin samples with respect to other discrepancy. For example, coming back to Matthias' talk, are there thinning techniques that work with respect to the discrepancy on the sphere, or to even different settings? Could also be interesting to do some work. And last but not least, if you have a look at approximation methods, for example, in an IBC setting or something, then you all often work with function evaluations where you clearly need some points. And you could also try to use thin samples with respect to these methods and try to see how good or bad things turn out to be in a setting of this kind. So I think that's quite a lot open work which is still to do on this topic, and I found it very interesting to work on this paper, and basically this was everything I wanted to tell you. There are, at the very end, there I put down some literature for you, and yeah, thank you.
Thank you very much, Julian, for this nice talk. Let me applaud. Let's perhaps push the applause button for Julian. All right, thank you. Now, are there any questions from the audience?
Okay, so I'm Jordi Marzo. I have a question.
Please.
Can I ask you something?
Yes.
Can you hear me?
Yes.
Yeah, we hear you.
Okay. So it's just that I was wondering how these results compare with other methods like this jittered sampling or other determinantal point processes. Do you know anything about this?
If I remember right, if you do this jittered sampling, you kind of first split the unit cube into those little boxes, and you say at least every box should contain one point or something like that. And this is, if I go back to the where I gave the densities, this is not the case here, because these densities you see in the lower bound, they never get 0, so you still have some small probability that you also get a point in some small rectangles or boxes where you already have enough points. Clearly, we try to minimize it, and this is why I think in the numerical simulations the greedy half strategy performs better, because then you somehow set the probability to 0 on those rectangles where you think there are already enough points. I hope this answers at least a bit to your question.
Okay, so you're saying that this strategy will be better, will give better results?
I don't know. At least the simulations seem to perform better.
Okay, because at least on the sphere, this back result is precisely using this jittered sampling, no, the upper bound.
Mm-hmm.
So,
Sorry.
so this back upper bound for the discrepancy on the sphere, it uses this jittered sampling. So I was wondering if
Yeah, I haven't studied on the these thinning strategies on the sphere, so I cannot say too much when it comes to discrepancy on the sphere.
okay. Thank you.
Thank you, Julian. Any more
So
questions?
I think, yeah, a little comment so regarding what Jody was asking. I think the difference, well, my understanding is, correct me if I'm wrong, is that here we consider online thinning so that we cannot go too far back. So I think the distinction with what Beck does is Beck seems to look at the entire configuration, and here the authors want to consider points as they are coming in. So this seems to introduce some difference, right? So here, what we want to do is we look at, so this is basically a greedy algorithm. We look at points one by one as they come in, right? Whereas Beck says, let's find the configuration which achieves minimal discrepancy. Yeah, and for that he indeed uses jittered sampling. So this seems to introduce some difference.
But I think the question wasn't about what the difference
okay,
is
the
between
quality.
methods.
The
The question
yeah.
was just like, what is looking at the final bound you get?
Right.
Is one giving you a better bound than the other? I think that was the question.
Yeah. Okay.
yeah, I think
Yeah. I cannot attest
maybe
the quality. Yep. That's a question for Julian. Yep.
maybe a short comment from my side. I think on the sphere it's good possible that jittered sampling is just better, but on the cube, if you consider this kind of discrepancy, it's probably already hard to find some disjoint, how to say, covering of the unit cube that you use for your jittered sampling, right? If you just take the regular grid, then the order of convergence of this point set that you produce with jittered sampling is already bad in the polynomial order, right? So here the result is you have a logarithm only. So the discrepancy is very good of this sequence. Although, so you only throw away every second point, at most every second point, and this makes a uniformly distributed point set, which is quite bad in N, to a quite good set in N. So I think it is a remarkable result in the case that you really only get a logarithmic discrepancy. I'm not sure that this is possible with jittered sampling.
Thank you all. Perhaps any more questions?
I had a question about something that was said at the end. So I've read parts of this paper, but not all of it. I didn't actually read about like the greedy HAR algorithm that they were talking about. But so you were saying, so what they do is they just actually it's perfect that we're on this slide. So you were saying that they still use this rho of t, but instead they've gotten rid of this normalization factor.
Yeah, they don't. The greedy HAR strategy, they do not create densities. So it's just a real thinning strategy, if you want to call it like this. And so they measure just by using this sum without the normalization and no densities at all. They just use this sum to measure if a point is good overall, if he is good for most HAR functions, because then since inside here you can only get plus or minus 1. So if the sum overall is negative, then you would say, okay, it's negative for most parts of it, and this can only be the case if the point is good for most half functions, which we consider inside here. And if the sum is positive, it's just the opposite. And this is just a criteria to whether to reject or keep a point.
Okay, but so at that point, I guess that they're throwing most of like the probability work that they were using in the original proof out the window. Because as you said, because it's not a density anymore. So like, right, they can't do things as probabilistically anymore.
I don't know if it's a density anymore. One would have to look at this. At least what they do is they just write down how to keep or reject points. But I don't know if one could, I mean, the density then would get 0 sometimes, I think. But one would have to look if everything is still okay in order to get a density, and then in order to do this balancing thing. I mean, where I probably could imagine there are some issues is here, because if a density gets 0, you cannot have this lower bound. And as far as I know, you need it to prove this, and you need this to prove this, and so on. So it probably gets complicated, but nevertheless, it could be done, and you could get very nice results, which are, yeah, I mean, what do they conjecture? They conjecture that you can kill quite much here in the exponent. But I think you need to do some different stuff.
All right, thank you very much. Any more questions?
Yes, I do have one more, and like it's mostly a curiosity thing because I've been playing around with this a little bit recently. So actually, kind of still related to the same slide, when they're doing that summation with the Haar functions, right? So they take the sign of the measure. They take the sign of when they're taking the inner product of the measure and the Haar function. If the normalization were different, do you think anything might come of if you, instead of taking the sign, just took that inner product of the measure and the Haar function? Somehow, in my mind, that would mean that somehow when you take the sign, you're just saying one side has more points. But if you remove that sign, then when you take that inner product, you can say, like, not only does one side have more points, but you can say how many more points that one side has. Do you know if there's been any like looking into that?
I have not tried this either, but I also thought of it when I went through the paper. So you're talking about here.
Right, just removing the sign function.
But I think one would have to check very carefully if you still end up with a density in each case, and if there cannot happen strange things, like at some point you might get some points which just yield a negative value. And I think if this does work, it could be better, because you somehow also take into account not only there are more points here than here, but also there are many more points here, and you even make the density even larger on the set, which is bad. I think that was the idea you had, if I right.
Yeah,
So,
yeah.
Ryan, also maybe a comment from my side. I also played around a little bit with this density and so on, and I failed. Maybe I tried 3 or 4 choices by letting that grow together with this, counting measure or so on. But the problem is this plays a role on in two aspects. First, you want to prove balancing, and if you do what you want, then maybe you get a better balancing result. right? So you get a better balancing for small half functions, or so on and so forth. You can play around a little bit, but then at the end you make this Markov inequality thing. And actually every weight that you introduce in your row then comes back to you, because, and so you have to play this out, right?
Mm-hmm.
And I tried several, so something like a polynomial decaying, something, because you could add, instead of the sign, you could add just a counting measure to some power or something, right? Or
Sure.
you can do something. And I tried some of these and I failed, and then because all these calculations are quite long, then I didn't. so I stopped at some point, right? So
Sure.
I wouldn't say it's not possible, but this is for some strange reason a very clever choice. So it makes every computation very easy looking, at least.
Yeah, just let me add one thing to what Mario just said. Also in this lemma, if you have a look at the proof, how they do it, you can also see it's balancing for all values which are smaller or equal to exactly this value.
Right.
But not if they are larger. So this is also very sharp. And I mean, this comes exactly from this normalization thing. And I don't know if then you could still prove the lemma exactly in this form. Probably not. If you increase at some point the balance, or if you increase the normalization factor, that you get larger probabilities of points falling into bad sets.
Thank you.
Thank you, guys. So any more questions? Okay, if it's not the case, let's perhaps stop the recording and ask again.